All right, we're going to pick back up with number 16. So we're going to take the derivative of exactly what's next to the natural log. So you've got dy over dx equals, so it's always 1 over a rewrite. And theta in this case is the variable. So we're taking the derivative not with respect to x, but with respect to theta. So it's dy over d theta equals, so we've got 1 over a rewrite, and then we're going to multiply by the derivative of this sine natural log theta. So this is kind of where it brings us into the next section, which is chain rule with trigonometry. So the derivative of the quote-unquote outside for the derivative of this trig stuff, the derivative of sine is cosine. So we've got cosine natural log theta, and then we're going to multiply by the derivative of this inside. So this right here is the inside of the whole thing. And the derivative of natural log, it's 1 over a rewrite, multiplied by the derivative of theta, which is our variable, the derivative of theta, which would just be 1. So I'm just going to go ahead and leave our full answer. You can leave it like this. You could also combine this. So this divided by this, cosine over sine is cotangent. So you can change this to cotangent of natural log theta, and then all over theta. That's actually the full simplified answer. So kind of leading into trig. So number 16 was the hardest one so far that we've done. But with trig has to have some sort of variable within it. Otherwise, it's a number. So if it just said tangent of 2 as y, the derivative of that would just be 0, because tangent of 2, that's an actual number. You could type that in your calculator and get an actual number. So this is really tangent of 2x. We're taking the derivative tangent of 2x. So we've got f prime of x equals. So you're going to take the derivative of the outside. The derivative of tangent, as we learned from trig, is secant squared. And then it's always a rewrite of the inside, right? The derivative of the outside. And then you're going to multiply by the derivative of the inside piece. So we've got times 2 in this case. So our final answer, you cannot multiply those together. That is wrong. You could just move this 2 to the very front. So it would be 2 secant squared of 2x. And that's our final answer. And number 18, so we've got to take the derivative of f of x equals 3 cotangent 2x. So I'm going to go ahead and put parentheses around that 2x part. Most of the time you will not see it with parentheses, but I like to put it just so that it shows the inside. So we've got f prime of x. And anytime that you have a constant, you're going to just drop it straight down. So we've got 3. And then we're going to take the derivative of the outside. So anytime that you take the derivative of c's, it's going to be negative. So we've got negative cosecant squared of, and then it's a rewrite, 2x. And then you're going to multiply by the derivative of what's inside. So this right here is that inside piece. So we've got times the derivative of 2x, which is just 2. So this is the full derivative. I can go ahead and multiply 2 times 3, and we could include that negative sign. So it's really negative 6 cosecant squared of 2x. On the next problem, we're going to take the derivative of x. So I'm going to go ahead and drop down the 2. The derivative of the outside, so in this case we've got the derivative of secant, which is secant tangent. And I'm just going to rewrite that 3x on the inside. So we've got secant tangent. And then we go ahead and take the derivative of the 3x. So when we take the derivative of 3x, we get times 3. And I can go ahead and multiply this 2 times the 3, and we get 6 secant 3x tangent 3x. Starting at number 20, it starts to get a little bit confusing because I know it doesn't seem like it, but the exponent of 2 is actually the outside part of this function. So this is also a chain rule problem because the derivative of the outside involves this 2. So you're going to take the 2 and you're going to multiply it to the front and then subtract 1 just like normal. So you're going to write down 2, and then it's cotangent to the power of 1 of x. So that's the outside. Now you're going to multiply by the derivative of the inside. And the derivative of the inside is that blue part, cotangent x. And the derivative of cotangent is negative cosecant squared x. So this whole thing is the derivative of using chain rule. So we could just rewrite this as, so I eliminated the 1 right here. I just erased it because we don't necessarily need it. So you could just move things around and you get negative 2 cotangent x cosecant squared x. Just make sure that when you take the derivative of anything with a c, it is negative. All right, same thing with number 21. So the outside is that 3 part. So you're going to take the 3 and you're going to multiply it to the front and then subtract 1. So we've got 3 in front and then subtract 1. So it's really 3 and then secant squared x. And then you have to take the derivative of secant x. The derivative of secant is secant tangent. And from here, you could multiply secant times secant to get 3 secant cubed x. Tangent x. Number 22. All right, there's a lot going on in this one because we've got the 4 and we've got another inside. So the first inside is the fact that it's sine. Sine is inside because the outside is that 4, the exponent. So you've got an inside of sine and an inside of 2x. So we're going to go ahead and start with a derivative of y dy by dx equal. You're going to take the 4 and multiply it to the front, and then you're going to subtract 1. So you've got 4, and then it's an exact rewrite, sine, exponent, new exponent's 3, so it's sine of 2x. So this entire thing is a rewrite except for the 4 and the 3. Next up, you're going to multiply by the derivative of sine 2x. So the derivative of sine is cosine, so you've got cosine, and then I just go ahead and write down the 2x, and then you have the derivative of the inside, most inside, which is a 2. So you can go ahead and multiply the 4 and the 2, this 2 and that 4, for an answer of 8 sine cubed 2x cosine 2x is our final answer. From here, we can just start inputting values so we can actually find the slope of cosine x over 2 and evaluate the instantaneous rate of change at pi. So we've got f prime of x equals, this is a little bit tricky, but the derivative of, we have the outside, which is cosine, so we've got negative sine, and then it's an exact rewrite, so we've got x over 2, and then you have to multiply by the derivative of x over 2. So you can think about this as, this is the same as 1/2 x. I just moved the x over. So dividing by 2 is the same as multiplying by 1/2. And the derivative of 1/2 x is 1/2. So our, you can plug in pi. So we have sine of pi over 2, which is 1, multiplied by the negative 1/2, and we get negative 1. Another inside and outside. So that is the inside. Take the derivative of the outside. So we've got f prime of x equals secant tangent, and then multiply by the inside, which is just the 2 right there. Please make sure that you are just rewriting that 2x right next to it. And then you can go ahead and input the 5 pi over 6. And when you input 5 pi over 6, do the math and you end up getting negative 4 square root 3. The remaining problems are just like a whole lot of bonus problems just to kind of do, and all of the answers to this entire packet are in focus. So if there's anything that you would like to go back to, you're definitely welcome to. But we're just going to kind of skip around through a couple of the problems, starting with number 25. So first of all, you could rewrite this as a double angle identity, except for when you rewrite it as double angle identity, take the derivative, you're going to have to use another double angle identity. So we're just going to go ahead and go for the exponent right here. So take the 2, multiply to the front, and then we have cosine x except for then you have to multiply by the derivative of the inside, which is cosine, so that turns into negative sine x. And then you've got minus, take the 2, multiply to the front, then take the derivative of sine. And from here, you've got negative 2 cosine x sine x minus 2 cosine x sine x, which just turns into negative 4 cosine x sine x, which then is letter E. Question number 26. This just involves a couple of different derivatives. So we're going to take the derivative of the exponent part first. So we've got 2 tangent, and then subtract 1 to get 1, tangent of e to the x, and then multiply by the derivative of tangent, which is secant squared. Again, we're just rewriting e to the x, but then you have to multiply by the derivative of the inside. Derivative of e to the x is just e to the x. The only one that matches up perfectly with that is letter A. In number 27, when you are doing these problems involving chain rule, please make sure that you are just rewriting the square root as an exponent of 1/2, so that when you take the derivative, you're multiplying the 1/2 to the front. And then subtracting 1 to get 1/2, but then multiply by the derivative of the inside. So 2t plus 2. This 2 can go ahead and cancel out with both of those because even though this is together, the 2 goes into both 2's right there. So really we have s prime of 2 equals, that'll be 2 plus 1, 2 from right here, plus 1, divided by, and then that's the square root of 4 plus 4 plus 8. So we've got 3 over the square root of 16, which is 4. Some other bonus type problems are on this next page. I like number 34 a lot. Just to recap, we get y by plugging in the -1, so it's e to the -3. Then make sure you use your exponent rules and change that into 1 over e cubed. To find the derivative, we've got to rewrite natural log of the base, natural log of e is 1, multiplied by the derivative of the exponent. And then we can go ahead and input -1. So we have 3e to the -3, and then we're going to have to change this into 3 over e to the +3. So the equation of the line is going to be y minus 1 over e cubed equals 3 over e cubed times x minus -1. The next one that I really like is number 35. So this says take the fifth derivative. And as we've been working with, anytime that you have a variable right there with another variable, okay, so k is actually a constant, not a variable. K represents a constant. So when we take the first derivative, so we've got dy over dx, we've got a rewrite multiplied by the derivative of the exponent, which the derivative of kx is going to be the constant k. So really we have k e to the kx. The second derivative, d squared y over dx squared, would be drop down the constant k, and then it's a rewrite, e to the kx multiplied by the derivative of the exponent, which is k, which means that we have k squared e to the kx. So if you're wondering why I just took a second derivative, right, it's because this notation right here means that we need to get to a fifth derivative. So right now I'm on 2. Here's 1. This is 2. And if we were to keep going, drop down the k squared. E to the kx multiplied by k. The third derivative turns into k cubed. And if we continue on and on, we should end up with letter B. 36 is a great problem because we're starting with h of x right here, and then it just involves a whole bunch of different rules. So to start, we have chain rule, and then once you do chain rule, you've got 2 terms, which means that you have product rule. After that, you can go ahead and use the givens and replace it. So really we have 2 f of x, g of x, that, g of x times g of x, this, and then negative f squared e.